Okay, we're going to be looking at graphs with discontinuities. I need that. Let's get rid of that. Right. So what does that mean? So let's imagine we hit a ball with a bat or something, and I'm doing my colour because pink on pink won't work. So here's our. It's going to bounce off a wall. Okay, so we've got a ball, and it bounces off this wall. And then the ball's going to bounce off and come back to us. So let's think about what that means. So we've got our velocity and we've got our time. Now the ball bounces off at some velocity and it goes at a constant speed, and then it hits this wall and it suddenly goes back. So in this point our velocity is positive, and here we've got a negative velocity. So when it bounces back, it's as if we have a sudden change in our motion. This is what we call discontinuity. So now we've got, this is positive v, and here we've got negative v, and then the motion continues. Now for this to happen, normally if you were to go from positive to negative, for such a change in motion you would have a deceleration and then an acceleration. In this scenario we're assuming that this happens instantaneously. In reality, for a change to happen like this instantaneously, you would need an infinite acceleration and deceleration to occur, which obviously isn't the case. But in these scenarios, what happens is the acceleration deceleration is so quick and happens over such a short time that it's negligible for the kind of examples that we will be doing, and we can therefore assume that this discontinuity is happening instantaneously. If you were to look, I'll just draw, imagine a floor, you've got a nice spherical ball bouncing and it bounces back up. In reality, what happens is when it hits the ground, the ball kind of deforms a bit. Or if it hits a racket, the racket hits the racket and then bounces back. You would see, if you were to look straight on, the racket kind of deforms a little bit, and it's this deforming of shape which is the deceleration and then the acceleration as it bounces back that we have. It's really useful if you go into YouTube and search for videos in slow motion. You can actually see this morphing. If you look, you can see videos of a golf ball being hit, and that the golf ball, although it's such a hard solid object, you can see it deform when it's hit by the hard club. So what would this look like for our displacement graph? Now, displacement, we don't get this discontinuity. So here, we've got the ball coming. It leaves the hand and it moves away. Its displacement from point of origin increases. And then we get this point here. And at this point where the motion bounces back, well, the ball, it starts to come back towards its point of origin. So we have something like that. Now we're going to look at an example of this of a kind of question that we would deal with this. So we're going to think of a ball travelling at a constant speed of 10 meters per second for 2 seconds until it strikes a wall. It bounces off the wall at 5 meters per second and maintains that speed until it reaches its point of origin. Then it begins to decelerate. It's not useful to decelerate at 1 meter per second squared. So we want to find the times and displacements. Okay, so we've got our wall. Starts here. This is our point of origin. Our ball starts with V1 at 10 meters per second, and T1 is 2 seconds. Then it comes back off here at V2 is 5 meters per second. We don't know what T2 is. And then we've got this displacement here, which is the same for the first point of the motion and the second point. And then after here, our ball begins to accelerate. Well, it's decelerating, so it's -1 meters per second squared for some time t until it'll come to rest. So our final velocity is going to be 0 meters per second. So first of all, because the velocity is constant here, we can find that displacement because the velocity is going to be s over t. The velocity is 10 over some displacement over 2, so s must be 20 meters. So let's just put that there. Now we don't know what t2 is, so again, because the velocity on this part of its journey is constant, we can use the same equation. So we've got this time 5 meters per second. It's the same displacement, which is 20 over t2. So t2, 20 divided by 5 must be 4 seconds. So that's going to be 4 seconds. Now here, at this point, we the initial velocity must be 5 meters per second because it starts at this point when it passes the starting point of its motion. So the starting velocity is 5 and its end velocity is 0. So we can use this to find out what the time is for the second part of the motion, because v is u plus at. Final velocity was 0. First velocity was 5. Our equals. Our acceleration was -1 times t. So the time for the second part, -5 equals minus t, so t must be 5 seconds. And then we're going to use s equals ut plus a half a t squared to work out the displacement. How far does it go? So our initial velocity was 5, the time is 5, plus a half -1, and t was 5 squared. So we've got 25, half of 25 is 12.5, and it's going to be -12.5. So that's going to be 12.5 meters, goes 25 minus 12.5 is 25.5. So that's our distance. Now, we want to sketch a velocity time graph and a displacement time graph. So let's do the velocity time graph first. So we start off at 10 meters, and this goes on for 2 seconds, and then we have the discontinuity, and it goes to -5, and it continues like this for 4 seconds. That's meant to be a straight line, so that's going to take us up to 6, and then at 4 seconds it starts to decelerate for another 5 seconds till we get to 11, and it stops. If you're drawing these, use a ruler so they're much neater than mine. And it's also important if for when you're showing acceleration and deceleration, if it's going to be curved, that you can see that it's actually curved because that is describing the motion, and it's not curved because you've not drawn it properly. That would not be good. So we are going to do our displacement graph. Now 0 here is our point of origin, so here. So we've got it going from the origin, and it goes 2 meters. Was it 2 meters? How far did we say S1 was? 20 meters, sorry. 20 meters, then it comes back. But it comes back more slowly, so that it takes longer. So this bit here is 2 seconds, and then this bit here was 4 seconds, so this is 6. And then it's going to reach -12.5, so we'll mark that here, and that's at 11. But it does so kind of, there's a kind of a curve to it, which you would need to show. So you show, it's important to show that the gradients, this has got a steeper gradient than this, and this has got, because it's decelerating, it's going to be a curved gradient. So I hope that helps.